In this video, we discover orthogonal vectors and a way to construct them. Orthogonal vectors are another very important tool for solving your mathematical problems when coding games or similar applications. Welcome, I'm Alex. Let's get started. At first, we start with two vectors a and b as usual. Looking at those vectors a little bit closer, we can find a relation between them. Decomposing vector a relative to vector b gives us a parallel and an orthogonal part. Written as an equation, vector a equals a vector a parallel to b plus a vector a perpendicular to b. For short, we just say a equals a parallel b plus a perp b. In the last video, we discovered the scalar product, which is just the right tool we need to compute vector a parallel b. For this to work, we first need to compute the projection, which is a scalar value, the scalar product. In order to get the projection of a onto b right, b must be normalized first. Please remember how to compute the unit vector and how its length is always 1. The video linked in the upper right corner will help you refreshing your memory. The second step is to multiply the projection of a onto b by the unit vector of b. So we end up with a vector that has exactly the length of the projection of vector a along vector b. So finally, we can reorder the decomposition to gain the second vector a perp b. This method is named Gram-Schmidt orthogonalization and it works for multidimensional vectors too. Allow me to mention two issues here. The first is that we need two vectors for an orthogonal construction, and the second is that if the vectors a and b are collinear, this method does not work because there is no orthogonal part a perp b. Let's see if we can do something about it by looking at an orthogonal pair of vectors first. In advance to the next video, let us call the pair of two orthogonal vectors an orthogonal basis, which consists of the vectors ex and ey. Ex points in x direction while ey points in y direction, and both are orthogonal to each other. We could actually see both vectors differently using the polar representation. That is, ex could be written as a polar vector rotated 0 degrees, while ey could be written as a vector rotated 90 degrees. Please note that in our Cartesian system the polar coordinate always begins along the x-axis. Generalizing both equations, we yield a polar coordinate where ex and ey are polar unit vectors. Phi will rotate ex while tau will rotate ey. But since tau could be any angle, we need to impose a rule here. That rule we will define in the way that tau equals phi plus 90 degrees, so the orthogonality will hold. Having done that, we can rewrite the equation so that ex doesn't change. Ey on the other hand will become dependent on phi, so it will always change along with ex. And that change embraces the rule that it always rotates 90 degrees further. Since 90 degrees is a constant and will never change, we can simplify further by looking at all the trigonometric identities we have. There we can find one that exactly replaces the phi plus 90 degrees term. Tau rotated ey. Tau was substituted by phi plus 90 in order to keep them perpendicular. Now we can replace ey with a better looking polar coordinate we looked up in the trigonometric identities. A cosine of an angle phi plus 90 degrees will yield a minus sine of phi, and a sine of phi plus 90 degrees will yield a cosine of phi. How awesome is that actually? This means that ey can easily be constructed by exchanging the sine and cosine functions and adding a negative sign, where you will always end up with an orthogonal vector. You can check that it actually is always orthogonal by computing the scalar product of both vectors. It always equals 0. In a video about affine transformations, we will come back to this constellation. But for now, how can this simple but genius endeavor help us even further? Well, let's do another and final substitution. And that substitution is that we simply replace the polar components by x and y, so the cosine of phi will become x and the sine of phi will become y. Using this replacement, we can rewrite ey in a much more pleasing way. That is, ey becomes minus y in its x component and x in its y component. Isn't that a great discovery? We now can construct EY entirely out of EX, and those are still perpendicular to each other. Please check it by computing the scalar product ext EY. Now let us spiral into the essence of what this video is about. Having any Cartesian vector A, we can always construct an orthogonal vector to A using the formula just presented. Just swivel x and y negate the new x component. That's it. A very simple but genius way of constructing an orthogonal vector to any other vector. With all that theory, let's do an example. This time with some coding. We start by grabbing the current mouse position in window coordinates, and we store it in an internal variable. In the next step, we prepare EX and EY by just computing what we learned in this video. EX will be at the mouse, while EY will be the orthogonal vector. After that, all we need to do is render both vectors. First, we start with EX by drawing a line from the origin to the position stored in EX. Second, we draw EY, the orthogonal vector to EX in the same manner. And the result looks like this. EX is in red and EY is in green. Both will always stay orthogonal to each other. This example can be found on GitHub. The link is in the description. I hope this video will help you in your coding endeavors. Now you should be able to always construct an orthogonal vector if you are in need of one. We will cover some applications to this method in some later videos in the future. Until then, like, share, subscribe and comment. Bye now!